Hi gang. So I was working through some of the ESX topology build that we were talking about last week, and then I realized that maybe we were getting ahead of ourselves just a little bit. So I thought that I would go back and cover some ground so that you'd understand why we're doing the things that we're doing, and maybe give you another example as we work through the ESX thing. So I decided to take another whack at GENI and build a topology there, so it's a little easier to see what's happening and give you some examples, and I can do it in a much shorter time frame. And then we'll go back to our friend over there, the ESX. So let's talk a little bit about GENI and the Openflow controller SDN based topology that I just built there.
And we're back with SDN topology build phase 2. Now, it struck me as I was building this that some of you might be seeing the video and not really understanding or not really thought very much about why we're doing this and what SDN, or software-defined networking, is all about. So I thought I'd define a couple of the reasons for the hullabaloo and then move into yet another topology. SDN has some really basic reasons for coming to the forefront right now. One is that network design is very stagnant. You build it and then you walk away. It's also not considered a development environment. So if you wanted to change protocols or modify things on the fly, you can't. Nobody will ever tell you, sure, go ahead and play around with the network. This means that the network and network design really is falling behind every other aspect of our computing lives. We also don't have the ability to use the network as a research resource, and that's because we have privacy concerns, but it'd be really great if we could test protocols and test topologies against actual user data. The network also has the problem of not being able to be segmented, meaning that we can't really divide the network up into a topology for you and a topology for me. You go play with your thing, I'll go play with my thing, and we'll still run on the same physical network. So we really can't do that either. And SDN, at least as an idea, is to address all of these. The traditional architecture has a control plane and a data plane. So what happens is you manage it. You SSH or Telnet or console into a network device. You configure it, and then the control plane describes how packets and traffic is going to be forwarded. That is the stuff on the data plane. Very traditional way of looking at it is that you set it up and then you walk away. SDN says, well, let's separate out those planes. So let's have an active management plane, an active control plane, and we still have the data plane. And this gives us our opportunity to do things dynamically, get away from that static configuration, and also maybe gives us a chance to do some shared resources. So a very basic topology looks something like this, where you have a network element. In this case, I've got a software switch, and then this sort of external device called a controller. Now, whether the controller is actually physically separated from the software switch is really immaterial, but the idea is that it is a separate entity and that it can dynamically work with the network topology and the resources. Now, out at the GENI network, you can actually try this out. So this is an example of the topology that they have built out there. It's very similar to the one that I just showed you. It's got a couple of more hosts, and the controller and the switch are connected across what might be a public internet. So you can see these graphics, and you can actually go out and do the tutorial that I'm about to do on the GENI network. Previously, I've done GENI videos, and the web interface that they used to have was Flack, and it actually caught a lot of flack because it was a little clunky. So now they've got a new one called JAX. It's a much cleaner interface. They did a very nice job on it, and this is what it looks like. So if you're looking at the other GENI videos, it's just a different interface to get to the same resources. So what I'm going to do is I'm going to ask the GENI network, which is a research network for network innovation. I'm going to ask it to stand up a couple of VMs for me. We're actually going to do this with 5 virtual machines. So I'm going to have a controller virtual machine. You can see that on the right there. A virtual switch, that's the center of the topology on the left, and then 3 nodes. Alright, so now once I've done that, I have my virtual machines running. I'm going to SSH into them, and then on the the switch, OVS or Open vSwitch, I'm going to issue these commands. And all that these do is they add ports to the bridge, the ports that are connected to the hosts, and then I'm going to connect a controller via that set controller command. A vSwitch or a virtual switch is a little different than an Ethernet hardware switch in that you have to tell it what you want it to do. And so nothing is on by default. This is as opposed to an Ethernet switch that you might buy from a vendor, right? And you plug hosts in and everything just works. And this is what makes OVS sometimes a little challenging to work with, but it also is what gives it its flexibility, because you can tell it to do just about anything. So here I've issued the commands, and then I ran OVS vs control show, and you can see the build that I did with my particular switch. Now again, this is all in the tutorial. I want to give all props to the folks out at the GENI project office, because they built this tutorial, and I'm just running it as a demonstration for what we're going to do later on. Well, we built the switch, but we really don't have an operating topology. Remember that we're just getting layer 2 on its feet. So we're creating very much just a topology where the hosts are connected to each other. But the switch doesn't forward anything. It doesn't do anything until the controller tells it that it's okay. So I can ping between my nodes, but it doesn't work until I get the controller. So what I'm going to do is on the controller VM, same thing, I'm SSH'd in there, and I'm going to run the pox controller. That's that pox.py there. So it's a Python-based controller, and I'm going to give it that additional command. So here's what happens when you run the controller. You can see that it's going up, and immediately it starts learning, because what I had going on in the background is my nodes were trying to ping each other. Now the switch has been told, listen, anytime you see traffic, ask the controller if it's okay. And the controller has been told everything's okay, so tell the switch that it's all right. I didn't do any firewalling or any blocking. So here's what the topology addressing looks like. The controller is at 192.86.139.79, and the Openflow switch was at .80, and they're swapping the Openflow messages. All the hosts and the downstream interfaces were all on the 10net. Now hold on a second there, Hartpence. What's going on here? Is this some kind of secret? Well, really what's happening here is that the Python controller is really there to accept and provide some Openflow messaging. The forwarding layer 2 learning is really all there to tell the controller what it's actually trying to do, what it's trying to support. And again, we were trying to get a layer 2 switch up and running. We feed in another Python script, and this is just a code snippet from that particular L2learning.py. So once the controller's up and running, what happens is we've got these Openflow messages going back and forth, and on the Open vSwitch or OVS, we install flow rules. And so here's some examples. You can see in the bottom there that I was pinging and it didn't work. And I turned on the controller and all of a sudden it's working. And the flows that are installed actually are in the top image there. Now the flows have a lot of fields, a lot of tuples that are associated with them that identify that particular flow. And they're much longer than the image here. They uniquely identify the flows. Well, I've mentioned Openflow traffic a couple times. Wouldn't it be really cool if we could see the Openflow traffic? And you can. It's a little tricky if you've never done it before. So remember that I'm SSH'd into everything. So that means that I've got, this sort of command line interface. Now, what I'm going to do is I'm going to run something called xming. It's a X server on my machine. And then I'm going to allow X11 forwarding via my SSH connection. So in PuTTY, it's just a checkbox. And then via the SSH session on the command line, I'm going to issue the Wireshark command. And what that's going to do is push X data through the SSH connection. I'm going to get a window on my machine. And it actually works pretty well. You just have to remember that it's very slow. So be patient with it because you're trying to send video data over this SSH or at least screenshots over this SSH connection. The last note that I'll make here is that I was fooling around with a lot of SSH clients, and you have to remember that the SSH version 2 keys vary in format. So when I was using PuTTY, I had to convert it to PPK format. And here's an example of the Openflow packets that you can see. Openflow runs on ports 66, 33, and 34, depending on which end you're looking at. Now, in all candor, this is not actually an Openflow capture that I did in this tutorial. The Wireshark version on my VM was not new enough to understand what Openflow was. So this is actually a capture from another machine, but that's what it looks like when it's going across the network. Well, didn't we start this whole thing about ESX? Well, now that we have a better idea of our topology, remember that we're using, in this particular case, a virtual machine for the switch. ESX already has a virtual switch, so now we have to think about how we're going to integrate these virtual switches together. GENI also establishes the links between the nodes and the controller, so we have to think about how we're going to do that. Between now and the next video, think about how you would do that, and then I'll show you how I did it, and there's more than one way to build this, but that's what we're going to do. Well, thanks guys for listening, thanks for watching. I hope I'm helping, and hey, may your packets always reach their destinations.